And our next speaker is Bryan Black from the University of Texas.
All right, thanks everyone, and for your introduction, Chris. I'm really glad to be here today. I've spent 9 years at the Hatfield Marine Science Center, and my general theme is if it has rings in it, it's my domain. I've been trained as a forest ecologist and tree ring person, and now apply those techniques to growth increments in long-lived fish and bivalves. And the overlying theme here is using these long histories of tree rings as proxies, as indirect measurements in the absence of direct observations, and also to augment direct observations, and especially those that span a long time like we would have at the Andrews. And this talk is about some tree ring chronologies I've been developing in collaboration with others in the Western Cascades and Coast Range, and two of the broad stories that are emerging out of it. So I hope that this is a launching point for further discussion, and look forward to talking with people after this talk about these very preliminary and emerging observations. And so there is a global network of tree ring chronologies. Each of these green triangles represents a publicly available data set, so quite a broad reach across especially the temperate forests. And although there is still quite a large gap in sampling in Western Oregon, these green trees are publicly available tree ring sites that you'll notice are really concentrated at high elevation and also eastern sites in Oregon, usually because there's a heavy emphasis on climate reconstruction, and those sites have often been thought as being the best climate indicators. But that's at the expense of chronologies in the Western Cascades and Coast Range that might have different stories to tell and very different histories. And so over the past several years, I've been involved in developing chronologies at several sites right around the Andrews and on out toward Newport, here highlighted by these yellow tree symbols. And so a lot of these have been developed by Alan Tepley, a former PhD student here working with Fred Swanson. And I've done several on the Coast Range, and in the summer of 2014, Alan and I met out at the Andrews and augmented some of the sampling at sites that had rather low sample depth. So here we are coring this summer of 2014 at several of these super old growth sites, trees that could be up to 800 years old. And we could get to the middle of them with these 32-inch increment bores and get a nice long record. And this is an example of what the tree ring data look like for one of the sites after very meticulously dating all these increments and measuring them. And this is, again, what the data look like, where there's a strong negative exponential or age-related growth decline that occurs in these trees, which is very typical. And so the step here is to remove that age-related declines to try to generate some sort of chronology that reflects environmental variability. And so to do that, you can fit each of these measurements. Here's one measurement time series, can be fit with the negative exponential function, which is the red line. And then to remove that effect, you can simply divide the values predicted by that red line by those observed, the blue line. And this removes that age-related growth decline and leaves behind this variability that should be a reflection of the environmental events that this tree had witnessed over its lifetime. And then these trees can all be detrended, and that's what each of these gray lines is a different tree, different measurement time series, and then averaged together after being detrended to get kind of a stand-wide level of environmental variability that these trees have experienced. And you get this kind of pattern here at one site called Browder Creek, and so lots of variability over time at a range of time scales, including some long-term trends. And it turns out that these long-term trends, these really low-frequency patterns, and this rise over time is kind of unique to each different site. Various disturbances, fires, windstorms that may cause a long-lasting trend in growth, which we wanted to remove those to really look at the synchrony underlying the patterns across these sites from the coast on out through the Western Cascades. And so to do that, we found if we took a somewhat different detrending technique, rather than fitting them with negative exponential curves, but using these more flexible splines, cubic splines, shown here by the red line, you could remove some of that lower frequency processes and be left behind with some more decadal, multi-decadal scale processes through interannual. And it turns out that's where the real synchrony is among these sites, is whenever we put those together, you start to see patterns across sites. And just to compare what it looks like when you get a chronology from cubic splines versus negative exponential detrending. So there are lots of different ways to parse out these data, but to underscore the synchrony across these sites and what's being shared across the landscape, the chronologies with the cubic spline provided the greatest coherence. And here's what they look like for all these yellow chronologies. I'll show you what these look like for Western Cascades. There are 6 different chronologies, all of them Douglas fir with the exception of this Tamalich pool, which is incense cedar, and also for the Coast Range, 3 different sites, not quite as long-lived as the ones in the Western Cascades, but still providing exceptionally long records of environmental conditions. So one of the things you'll notice are these really severe declines early in the record, which appear to be very consistent with insect outbreaks, so a series of insect outbreaks from the 1200s through the 1400s, 1500s. And those are even consistent and coherent with insect outbreaks that have been described on the eastern side of the Cascades. And Alan's been working a lot with describing these insect outbreaks and spilling across the Western Cascades and their patterns across the landscape as one potential story from these chronologies. And I've been especially interested in long-term patterns of variability over time. And it appears that there are periods where the trees show exceptional amounts of variability and other time periods where there's rather some quiescence in this tree ring record. And I've zoomed in on a section from about 1600 to 1850 here to highlight one of those time periods that has exceptional variability, which is right around the mid-1700s, from about the 1720s to the 1760s. And you can see these look like earthquakes in the tree ring time series, like a seismograph that get lots of variability up and these tree ring chronologies, and it's shared from the Western Cascades clear on out through the Coast Range. And one of the most notable of these is highlighted here in 1739. There's a very prominent event that you could see in all the tree ring chronologies. It's just like the trees were growing and hit a brick wall. In fact, a lot of them would even be locally absent rings. The tree wouldn't even form a ring in 1739, and even 1740 and into 1741. It was a very prominent characteristic that we saw all along the western Oregon. And another one back here in the 1650s, though we didn't have anything from the Coast Range to really corroborate it. But still 1739 being a very major event that we've noticed, and surrounded by a period of extreme variability. It's notable that the quake and tsunami of 1700 didn't show up at all in the tree ring chronologies from the Coast Range. Even one of them was developed out here on the in Mike Miller, south of Newport, in collaboration with some teachers in training. With Kari O'Connell had a program through NASA to fund teachers to work with me to develop this chronology at Mike Miller, which was a lot of fun. And we thought for sure we'd see some effects of the 1700 quake, and we didn't. But we sure saw the 1739 event. And it was possible to quantify that roughly across the landscape, just taking the observed growth as the 1739 anomaly minus the preceding growth divided by the preceding growth, kind of an observed minus expected over expected, times 100. And that could graph out this response for our chronologies plus other publicly available chronologies. And the big red circles are those that showed the large growth declines in 1739. The biggest reductions, 40, 50% reduction in those years, 1739 to 41, and really centered here on the western Oregon region. And what's interesting is there's a network of redwood chronologies that's just come out, led by a group at Humboldt State, Alice and Carroll, and they found that 1739 is a huge marker in their redwood chronologies as well, especially from the northern sites up around the Oregon-California border. And here's one example. The asterisk is on 1738. And 1739 and 40 are completely missing, and the tree resumes growth in 1741 on up through 1750 with the double dots. So this seems to be something from the northern redwoods clear on up through the Western Cascades as the major event in the last 500 or 600 years. And it's somewhat interesting that this is coincident with a major climate anomaly, a little ice age anomaly in Europe, where 1739 through 41 there was this persistent high pressure that led to extreme cool conditions over Europe and a great famine in Ireland. And whether that's connected or not, who knows what that's doing with the jet stream or atmospheric conditions. But it's interesting to note such a prominent feature of the little ice age shows up here in the western Oregon forests that seem to be indicative from the tree ring chronologies. And another brief aspect of this work I'll talk about is Jason Dunham and I had developed a network of freshwater chronology mussels throughout Oregon. And we're also interested in river discharge and their influence on mussels and how mussels and rivers related to the trees. and in particular how trees could be used to hindcast hydroclimate in Oregon and expand our knowledge of what historical ranges of variability in winter hydroclimate in particular were like. So we had a network of river discharges from these sites here, each in these yellow diamonds as a river discharge of a rather natural river. And you can see what those look like here in terms of anomaly. There's a lot of coherence across those river discharge records, the black line being the mean, or if you take the leading principal component, it's just about the same and explains 78% of the variance, just to underscore that synchrony in terms of water year discharge across those river sites. And so we were real interested in seeing what we could reconstruct, and one of the rivers we chose was the John Day River, which has a nice long record to it. And this is a map or a plot of the correlation between each tree ring record we had available and river discharge there on the John Day, plotted on the x-axis with elevation. So there's a real strong elevational gradient that reflects how trees relate to river discharge in this especially winter hydroclimate throughout Oregon. Get these trees from the Coast Range, which don't respond very well. But others, there's this elevational gradient where at high elevation there's an inverse relationship. Lots of snowpack is probably bad. It delays the onset of the growing season, and so you get this negative relationship at high elevation. Positive relationships tend to be at the moderate to lower elevation sites. But you can use these tree ring chronologies to get an idea of what past variability was like in the hydroclimate, with the goal of relating trees to the rivers. So here the black line is a tree ring reconstruction, and the rivers in blue. And one of the complications we kept running into is that we get really strong relationships between trees and rivers late in the record. So this is what that relationship looks like with the biplot, r squared to 0.57, as opposed to early in the record where we found that the relationships just kept falling apart. It seemed much lower. Here the r squared's only 0.23, which concerned us a little bit because you like to have stability in your climate growth relationships. And as we began looking at the records, like this river discharge anomalies in the John Day, it appeared that they were becoming more variable over time, and that maybe this had something to do with the relationships with the trees, that there's stronger relationships. This more variable periods are driving stronger relationships with the trees than earlier in the record. So you could quantify this just by calculating the standard deviation in the 21-year record. So what's the standard deviation from 1906 to 26, stepping forward another year, 1907 to 27, and so forth, to get the running standard deviation of river discharge. And we found that it's quite common to have this run-up in variability in the river discharge, the John Day and other locations. In fact, this is what the running standard deviation looks like across all of our sites in Oregon. And we could do a comparison here of the early standard deviation versus the more recent standard deviation. And there is usually quite a step up in the amount of variability in the recent period versus the early period. And you quantify that again, the recent half of the observations minus the early half over the early half. What's our change here? And there is quite an increase in variability at a lot of these sites, with the pink and red diamonds indicate a strong increase in variability in this river discharge that we were noticing, pulling Washington into the picture. And we could do some simulations to see whether this is really unusual by generating data that has the similar autocorrelation and properties as river discharge. Do that 10,000 times and see how the differences in standard deviation look in the simulated data. And what we see in the observed data is that it is quite unusual to see this rise. It's not really what you would expect by chance. And so this got us thinking, especially about if there's rising variability, would that better synchronize river or hydroclimate and river discharge across the landscape? These extremes tend to synchronize things. And so I could calculate running pairwise correlations among all these rivers. And so I could begin in the early half, at least for where we have a complete record of all rivers. Back through 1946, we have complete records. What's the mean pairwise correlation among all these rivers? We correlate each river with everyone else. What's the mean correlation? Here is 0.56. And then in the more recent period, it goes up to 0.77. So there does seem to be more synchrony in the river discharge. And this could be done a little more elegantly by doing a running correlations in those rivers in 21-year windows. And so this is the running correlation, that the change in correlation among all those pairs of observations over time. And there is a bit of an upward trend to it. It would appear that this river discharge is becoming more synchronous over time, and at a rate that you would not expect by chance. And we could repeat this too using Palmer Drought Severity Index for the winter months from all the climate divisional data in Washington and Oregon, data that go from 1895 to 2015. And so again, we see this rise corroborated by the Palmer Drought Severity Index and synchrony in drought and in river discharge across Washington and Oregon, that it's being led to us by these trees. And even in California, we see these patterns as well. Winter sea level at 4 observations, upwelling in the California current, even split-nosed rockfish and blue oak chronologies all have this rise in synchrony over time, which we find very interesting. And so now the question is why? And one of the mechanisms could be the North Pacific High, which is really important to winter hydroclimate. The white box there with the H in it is the location of the North Pacific High, which can be very variable in the winter months and really affect the onshore flows of precipitation. And this is the correlation between the North Pacific High and gridded sea level pressure in the North Pacific. So you'd expect strong correlations where we correlate pressure with itself, right where the North Pacific High is. But when you look early in the record, 1920 to 1966, compared to later in the record, the correlation between the North Pacific High and the sea level pressure, you get this stronger correlations with the tropical Pacific. And the tropical Pacific has been rising in variability, especially ENSO, over the past past century. And so we wonder if this tropical teleconnection and atmospheric bridges are strengthening with the North Pacific High, and this is showing up in winter hydroclimate and biology. So, those are some of the things we're pursuing. Lots of great stories in those tree ring chronologies. What's the deal with rising variance that the trees would suggest? And, it's going to be important to update some high elevation chronologies to further pursue this, I think, in the Cascades. So with that, I've run over by a minute or two, but I hope we have time for some questions. Okay.